Welcome! In this video I'll show you how to solve problem 4.6 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now this problem states the following. It says, starting from the Rodrigues formula, derive the orthonormality condition for Legendre polynomials, which is what we have right here. And they give us a hint that we should use integration by parts. So that is what we want to do. And this is honestly simple in principle, but it's going to be a little bit messy. So what we want to do is simply plug in PL and PL prime, right, the Legendre polynomials, into that integral, right? Because if they are orthonormal, then we have to integrate over the entirety of the domain. And as we know, Legendre polynomials are only defined between -1 and 1. So that's why we're integrating over that region. And now we just plug in the formulas for PL and PL prime. So PL is simply 1 over 2L L factorial. Then we take L derivatives of x squared minus 1 to the L. And now we do the exact same thing, but for L prime instead of L. So we have L prime derivatives, x squared minus 1 to the L prime, so to the L prime, and dx. So here we can, of course, take these constants outside. So 1 over 2L, it doesn't depend on x. So we can just leave it in the front. So 2 to the L, L factorial, 2 to the L prime factorial. So what we need to do is somehow solve this integral, which, well, it looks nasty, I'm not gonna lie to you. So, well, what do we do here? Now, there are two possible cases. Either L is equal to L prime, or they are not equal to each other. Now, in the case where they are not equal, L can either be greater than L prime, or L can be smaller than L prime. Okay? Sometimes people want to choose right away which case you will commit to, but honestly, there's no real need. We can do it as we move along. So what we will do here is, as they suggest, just use integration by parts. So let's take this part and choose one of them to be u, one of them to be dv. It doesn't matter which one you choose. The only difference is that if you choose one, you will end up at the conclusion that L has to be greater than L prime. If you choose the other, you will get to the other conclusion. But in the end, it doesn't matter. They are dummy variables, right? You may as well call this L prime and this L without the prime. So it doesn't matter. Right, so it's completely arbitrary, just pick whatever you want. I'm going to pick this first one as my u because, I don't know, it appears first and I like that. So u will be d dx to the L, x squared minus 1 to the L, which means that du will be the derivative. And notice how easy it is to take the derivative because we are taking the derivative of something that was derived L times. So simply derive it L plus 1 times. See, very easy. And this is unchanged, right? Because this is simply the thing we are taking the derivative of. We don't have to explicitly calculate it. Then we have dv, which is also going to be, well, there is no change here, of course. This is dx, by the way. And then we have x squared minus 1, L prime dx. And v is very easy to calculate because it's simply one less derivative. So that means that it's going to be L prime minus 1. X squared minus 1 L prime. So this is our integral here. So let's go for it. And just for simplicity, let's just keep all of our constants outside. So goodbye to all those constants. Let's just worry about the integral itself, which I will call I. So that's I. So I is going to be the multiplication of these two terms. So we get, that's the boundary term, d dx. We derive L times. What do we derive? X squared minus 1 to the L. And then we multiply this by the L minus 1, so L prime minus 1 derivative of x squared minus 1 to the L prime. And we evaluate this between -1 and 1. And then we still have the integral. So we integrate from -1 to 1 of these two things. So that would be the L plus 1 derivative of x squared minus 1 to the L, and then we still have the L prime minus 1 derivative of x squared minus 1 L prime dx. So notice that what we achieved by doing this is reduce the amount of times we take the derivative here and increase it there. Now, both of them can be quite useful because if we reduce it to 0, then we are not taking derivatives anymore, and it's quite simple to work with. And if we go to a very large number, then we're not going to have a polynomial anymore because each time you take the derivative, it goes down in order. So both of those outcomes are quite good. But the problem is that we are not done, right? If L is a large number, we may have to do this a lot of times. So let me show you how to do this one more time, and then we will try to come up with a general formula to do this n times, and then go to the limit case and see like, where do we run out of possibilities. So let's just show you, let me show this one more time. So first, boundary term 1 is what I will call that. Because I'm lazy, I will not write it again. Then we have plus, let's see. And now we need to take into account, and actually I think I'm going to write this a little bit further down, because we are going to integrate by parts again. So let's say this is equal to boundary term 1, which is this. That. So now to integrate by parts again, let's again choose this to be u. So u will be the dx L plus 1, x squared minus 1 to the L. Du is going to be, well, just one more derivative, so L plus 2, x squared minus 2, minus 1 to the L. And then we have the v, which is going to be, let's see, so that would be this other part. So we get, this thing is unchanged for now, so L prime minus 1, x squared minus 1 L prime, and this is dx, of course. This is also dx. And then we have v, which is going to be two derivatives now. So it's L prime minus 2. So x squared minus 1 L prime. Now let's do the cross multiplication here. So we get the first boundary term, and then we have another one, which is going to be plus. Let's see. Actually, wait. Plus, but keep in mind we have a minus sign here. So actually we have minus in front, and then we have this thing. So it's actually going to be a minus there. And then we have L plus 1 derivatives of x squared minus 1 to the L times L prime minus 2 derivatives of x squared minus 1 to the L prime. And then we have minus, and this is of course evaluated between minus 1 and 1. Then we have minus the integral from minus 1 to 1 of the product of these two. So there we would have taking L plus 2 derivatives of x squared minus 1 to the L times taking L prime minus 2 derivatives of x squared minus 1 to the L prime and dx, of course. So let's see if we can see a pattern. So let's say that we do this n times, right? Some number n. Okay, and n can go all the way to L or L prime. We don't know which one is larger yet, but it can go all the way up to one of those. So the boundary terms, we're going to have a lot of boundary terms. Every time we integrate, we get another boundary term. So we have boundary term 1 plus boundary term 2, which is this. And then we're going to have some more, right? Boundary term 3 and then 4, blah, 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 all the way until boundary term n. Right? And what is going to be boundary term n? Let's try to figure it out. So notice that the first time we did this, the first boundary term just had L in the exponent. But the second time we did it, it had L plus 1. And if you want to be sure, you can do this one more time explicitly to see that the third time you get L plus 2. So what we actually have is that the boundary term is going to be the dx. Oh, I didn't close the parentheses, by the way, so maybe let's close it. We have L plus n minus 1 times the derivative. That way, when n is equal to 1, we have L. When n is equal to 2, we have 1, and so on and so forth. So that does a good, it matches what we have. So this to the L, and then the other derivative, it's increasing every time, right? So The first time it's L prime minus 1, the second time it's L prime minus 2, the third time it's L prime minus 3. So this is simply L prime minus n of x squared minus 1 to the L prime. And this is something we have to evaluate between minus 1 and 1. Okay. And then we still have the integral. So what happens with the integral? So notice that in this second part, when we did this integration by parts twice, we have a minus sign in the front. So let's maybe multiply through. So let's just multiply through. So this part is negative, but this will be positive now. So the first time around, we had a minus sign in front. Now we have a positive. And next time we're going to get minus again, because each time you do integration by parts, you get minus the integral. So we have minus 1 to the n, right? The first time it was minus 1 to the 1, so minus the second one, minus 1 squared, so plus, and so on. Then we have the integral from minus 1 to 1. And each time we have done this integration by parts, we have increased the amount of derivatives by 1. So if we do the integration by parts n times, then we get L plus n. And we are, of course, still deriving the same thing here. And the other part, the other term of the derivative has been decreasing every time. So that means that we get L prime minus n of x squared minus 1, and I'm missing a little bit of space, dx. Okay, so this is what happens n times. Now, what happens if we go to the limit, right, to the absolute limit? The question first is, of course, well, what is that limit? How many times can we do this integration by parts before we actually get to the result? So, of course, well, maybe it's not obvious, but the way in which this ends is when this exponent ends up being 0, right? Both here and here. So that is the limit that's going to allow us to actually solve this. So that means that we want to go all the way until n is equal to L prime. Okay? So what happens in that limit, right? Let's say that n is actually equal to n prime. So in that limit, we have all our boundary terms, right? Boundary term 1, plus boundary term 2, etc., etc. And this is our boundary term L prime, which I will write explicitly because it's the last one, and it will give us some insight. So the last one will be the dx L plus L prime minus 1, x squared minus 1L, the dx, and then L prime minus L prime, so no derivatives, 0 derivatives. And then, well, we are taking 0 derivatives of x squared minus 1 L prime, and we evaluate all of this between minus 1 and 1. Okay? And notice quickly what this is. So before we write down this, let's just take a moment to think about what these boundary terms are. Because in the last one, it is quite evident. We are taking the derivative of this, and then we still have this thing remaining. So this is always going to be 0, because you evaluate at 1, it is 0. You evaluate at minus 1, it is 0. And what about the other boundary terms? For example, this thing right here that I will now highlight in green or put in a box, this right here was our second boundary term. But notice here that it doesn't really matter what the values of L and L prime are, because what you're doing is taking some amount of derivatives of this x squared minus 1. And x squared minus 1 is basically x squared minus 1 times x, so to the L, x squared minus 1 times x squared minus 1, and so on, L times, right? So if you are taking L derivatives, then you're still going to get some x's remaining, right? So even if you get rid of all of them here, for example, because here you're taking L plus 1 derivatives and then L plus n, for example, which is, well, n is L prime now. But here on the other side, the amount of derivatives is always decreasing. So here there will always be some x squared minus 1 remaining, because each time you take a derivative, you get rid of 1. But you're still going to have 1 in the end, because you're simply not taking enough derivatives. So for that reason, every single boundary term is also 0, not only the last one. And it is because you're evaluating at 1 and minus 1, and x squared minus 1 is always 0 at those points. So that means that all of the boundary terms, all of this is 0. So finally, we have the integral. So we have plus minus 1 to the L prime, right? We are doing this n prime times, sorry, L prime. And then we have integral from minus 1 to 1. Now notice, since we are integrating this thing, which is to the L prime, by the way, 0 times, that means we can just write it in the front so that we don't get confused that maybe it's getting derived there. So let's not get confused. So this means now we are taking L plus L prime derivatives of x squared minus 1 to the L dx. So what is this integral? The key part to look at is this. What we are doing is taking L plus L prime derivatives of something that is of the order x to the 2L. Right? And then you have, well, some number times x to the 2L minus 1 plus some other number x to the 2L minus 2 and so on. But since we know that L and L prime, right, they are not equal, we can now just see what happens in each one of the cases, right? What happens if L is greater than L prime, and what happens if L prime is greater than L? So if L prime is greater than L, then L plus L prime is greater than 2L. So in that case, we're going to take more derivatives than the number in the exponent of the polynomial. So all of that will be 0. Right? So that is a case that we really like, because that means that the entire integral is 0 when L is different from L prime, which really helps us get what we want, right? We want to show that the entire integral, right, is going to be dL prime. So if we choose the case where L prime is greater than L, then it's perfectly correct. And we don't really have to worry about the other case, because keep in mind we are using dummy variables. We could have done this entire procedure, but instead of choosing u to be what we chose, we could have chosen that thing to be dv and done the integration by parts the other way around, and we would get to this, but in the other case in which L would be greater than L prime. But in the case we chose, that is the condition. So if L is greater than L prime, then that entire integral, as we just saw, is also 0. So that means that all of this is 0. Okay, so when L is different than L prime, we see that this expression, right, this expression right there is 0, which is of course what we want. We want this thing to be true. Okay, so now we need to go check the case where L is equal to L prime. So that is now what we will check. So what about the case when L is equal to L prime? Well, let's just go into our expression right here, the one that we just wrote down, because we hadn't really said anything in particular here. So now the boundary terms, well, they are still 0 because it doesn't really matter what the relation is. You still have these terms lying around. So all of this is still 0 for the exact same reason as before. So now the interesting thing is this integral. So if L is equal to L prime, well, this is going to be L, this is going to be L, this is going to be 2L. So what is now that expression? Right? What is that derivative? So now we are taking 2L derivatives of something of order x to the 2L. Right? So that means that if we take one derivative, we get 2L x to the 2L minus 1. If we take two derivatives, we get 2L, 2L minus 1, x to the 2L minus 2, and so on. Which means that this derivative will simply be 2L factorial, because every other polynomial than the one with x to the 2L power will be 0, and this one, if you derive it 2L times, then you just get 2L factorial, because every time the exponent comes down and multiplies. So this entire thing right there is simply 2L factorial. That is 2L factorial. Okay, so this is now the integral that we need to calculate. So let's call it I2. Put the constants outside, so minus I to the L, 2L factorial. And actually, this is still I. I will call I2 the actual integral. So the integral is minus 1 x squared minus 1 to the L dx. So that is what we want to calculate. Now, there's one thing we could do actually, and that is put the minus 1 in here because they have the same exponent. So we can actually write this as 1 minus x squared to the L, and it looks a bit nicer, and we will have to do that for the integral anyway. So let's call this integral just I2. So how do we solve it? Well, let's use a little change of variables, a substitution, because we know that 1 minus x squared, if we have x to be a cosine or sine, will give us something trigonometric that will get rid of that 1 minus x squared. So for example, if we say x is either cosine theta or x is equal to sine theta, because of the fact that 1 minus cosine squared theta is sine of sine squared theta, and of course 1 minus sine squared theta is equal to cosine squared theta, you can choose any of these two substitutions, and you are going to get rid of that very annoying thing right there, which makes integrating very hard. So I will say x is equal to cosine theta and use that. And that means, of course, that dx will be minus sine theta d theta. So by doing this, we get integral, and what are the limits? At minus 1, if x is minus 1, cosine theta has to be pi. And if x is 0, then cosine, so if x is 0, then, no, sorry, not 0. Yeah, that was weird. No, if x is 1, yeah, I was like, what? No, if x is 1, theta has to be 0. There we go. And then we have 1 minus cosine squared of theta to the L times minus sine theta d theta. Now, of course, 1 minus cosine squared theta is simply sine squared. So this is sine squared. And sine squared to the Lth power is simply sine to the 2L power. And we can use the minus sign to reverse the limits of the integral. So that goes from 0 to pi now. Okay, so this is what we now have to solve. And it may look very, very, very difficult, but it's actually quite okay. So what we will do here is use integration by parts and choose this to be u and this to be dv. Why? Because since sine theta is to the power 2L, every time we take a derivative, the power will go down, and you will see that we will be able to get to a recursive formula. So you will see that very, very shortly. So if we take u to be equal to sine theta to the 2L, then du is going to be 2L sine of theta to the 2L minus 1 times the derivative of sine, which is cosine theta d theta, and dv is simply sine of theta d theta, which means that v is the integral of this, which is minus cosine theta d theta. Okay, so now let's plug it in. So that means that I2 is this cross product there, so minus cosine theta. Sorry, I don't know why I wrote this d theta, by the way, so that's of course not there. Minus cosine theta sine theta to the 2L evaluated between 0 and pi, which is 0 because sine theta is 0 at both ends, so goodbye to this. And then we have this other part, which will give us minus minus, so plus, integral between 0 and pi of 2L, which I will write outside. And then we have sine, sine of 2L minus 1 of theta. I wrote it a bit weird, but you get what I mean. Times cosine theta squared, right? Because we're multiplying those two, so cosine squared theta d theta. So that is what we get. So it may not look like progress, but in fact we know that cosine squared theta is, right, cosine squared of theta is simply 1 minus sine squared of theta. So plugging that in, we get that this is 1 minus sine squared theta. So now we can multiply. So we get 2L, factor of integral from 0 to pi, sine of theta to the 2L minus 1, d theta. So that is this first part, so with a 1. And then we have minus the integral from 0 to pi. And now we have sine to the 2L minus 1 plus 2. So we get sine of theta to the 2L plus 1 and d theta. And notice that this is precisely what we started with. It's exactly the same as that. So this I2, keep in mind, is precisely integral from 0 to pi of sine of theta to the 2L plus 1 theta. So we can now add this, right? Take it, put it on the right side. So we get 2L plus 1 factor of the integral from 0 to pi sine theta, the 2L plus 1 theta. This is equal to 2L integral from 0 to pi of sine theta to the 2L minus 1 power d theta. Okay, so basically what this means, and especially if we divide by 2L plus 1, let's just divide by 2L plus 1, we can see that if we have an integral with an odd power of sine, we can write it as 2L over 2L plus 1. Why does it looks like 10 because of the lower limit? There. 2L divided by 2L plus 1 times the integral of sine, but then the next lower odd power of sine. So if you have sine to the 5th, then you get sine cubed, and then you can do it again to get sine. So we got a recursive formula, right? So the integral for 2L plus 1, the power 2L plus 1, is 2L times over 2L plus 1 times the integral for 2L minus 1. But now if we plug in 2L minus 1 instead of 2L plus 1, notice that if we had 2L plus 1, we had to multiply by the number that we put in minus 1. That's why we have 2L and not 2L plus 1. And then we divide by the same number. So if we want to go for the next one, we have 2L plus 1. This is this one, right? And then from this integral, using our recursive formula, we have 2L minus 1. Right? That's the next, sorry. If we input 2L minus 1, we get 2L minus 2. There we go. Okay? And then down here, we get 2L minus 1. And we multiply by the next one, which would be 2L minus 3. So if we want to just keep going, here we can go for, well, what we already had, 2L plus 1 times 2L minus 2, 2L minus 1, and then, well, the next one, the next one, the next one, the next one, and eventually you're going to get to the very last possibility, which is 2 over 3, right? The lower number is always one more than the upper one, and then times the lowest possible power, which would be 1. So I1. Now the question is, well, what is I1? That will simply be the integral from 0 to pi of sine theta to the 1 power, which of course we know how to integrate. That is simply minus cosine of theta between 0 and pi, which will be minus cosine of theta at pi, which is minus 1, minus cosine theta at 0, which is 1. So we get 2. So I1 is simply 2. So we get times 2. Let me get rid of this because it was just to make a quick calculation. So now the question is, well, how can we write this in a more compact way, right? Not just as this product of so many terms. Well, notice what we have. We have 2L plus 1, 2L minus 1, 2L minus 3, 2L minus 5, all the way down to 1. So this kind of looks like a factorial, except we are missing some terms. So, well, let's produce them. So we have 2L over 2L plus 1, and now in red I will produce the terms that it needs. It needs the term 2L, so I will multiply by 2L over 2L, which is 1. Right, that way I have 2L plus 1, 2L. And then I have a term that I already had, 2L minus 2 over 2L minus 1. And then I don't have 2L minus 2, so let's produce it. 2L minus 2 over 2L minus 2. And then I would have the term that I already have, which is 2L minus 3 over 2L minus 3, and so on and so forth, until eventually I go all the way to 2 over 3, and I would have to produce here 2 over 2, right? And times this last 2 that comes from there. Okay, so what is this? Well, in the denominator, it's quite clear. I have 2L plus 1 factorial. Right, I think that's pretty evident. 2L plus 1, 2L, 2L minus 1, 2L minus 2, and you always produce the ones that you don't have. And notice that the ones that we didn't have, are always the same that we already had in the numerator. So we got 2L, 2L, 2L minus 1, 2L minus 2, another 2L minus 2, and so on. So what we could do would be to factor out a 2L in the numerator. Just 2. We factor out 2. So that means that we would get 1, 2 from the first one, right? 1, 2 from here, 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 1, 2 from here. So basically we're going to have 2L times however many numbers we have 2L2s, right? Because we have 2 of each one and we have L of each. So that's the way that it goes. So we have 2 to the 2L. And once we do that, we have L factorial left. Right? Once we do that, we have L factorial left 2 times, right? Because we have 1L here, 1L here. This is now L minus 1. And this is L minus 1 again, right? This is also L minus 1. And so on and so forth. So each one that we end up having is just going to be... Oh, by the way, I made a quick mistake here. This is, of course, 2L minus 4. I'm sorry about that. That's, of course, 2L minus 4. It has to be. So I'm sorry about that. I will try to add a comment later. So that is 2L minus 4. So now this is simply L minus 2. And we will have 2 of them because we had to produce one for this. So blah, 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 right? So we just continue going. And that means that we have L factorial squared. Or we can just write this as 2 to the L and L factorial squared. So 2 to the L times L factorial and all of this squared. Times 2, of course. This little 2 that remained. Okay, so this is the integral. Now, where was this integral? So let's go all the way back and plug it in. So this integral first appeared there. And we still have to include that. So that is what we still need to do. So just multiply this by what we had before. So I'm just going to write this minus 1 of PLX, PL prime of X. This is this times 1 over 2 to the L, L factorial, 2 to the L prime factorial. But we are in the case where L and L prime are the same, so just get rid of the primes. And notice that this perfectly cancels out with this. And there's another term that we kind of left behind, right? We can go back a little bit. And it is right here. This 2L factorial. So we still need to include the 2L factorial. So we still have 2L factorial. And notice we have 2L factorial over 2L plus 1 factorial. But 2L plus 1 factorial is simply 2L plus 1 times 2L factorial. So this is simply 2 over 2L plus 1. And now we keep in mind that this is only valid when L is equal to L prime, which means, of course, that we need to add delta L L prime. Because when L is not equal to L prime, this integral was 0. So there it is. We managed to prove the orthonormality condition. This is exactly what we wanted to prove. And yeah, it was a bit of a long way, but we did it. We did it. It was not easy, but we did it. So congratulations if you made it this far. And yeah, if you enjoyed the video and if it was useful, please consider leaving a like on the video, commenting and subscribing, and maybe even consider checking out my Patreon. So I'll see you on the next video. Thank you very much for watching.